Welcome to Lecture 7 for International Regulatory Frameworks for Climate Change and Environmental Management. So in this lecture we are looking at the protection of the ozone layer. So in our last lecture, you recall, we were looking at United Nations Convention on Law of the Sea, 1982, and we're in the 1980s. So in this lecture, it's a short lecture. Ozone layer, the ozone protection is relatively simple to understand, and there's only a few key things that are broadly important for everyone to understand, even if you're not working specifically in the ozone regime. If you are, then it's very technical, a lot of chemicals involved, and the regulation of them. But for general purposes, just a broad understanding about why this is such a success story is the important thing that I want you to take away. So we're going to look at the ozone layer and ozone depleting substances. So a bit of an overview of the science and the issues, then to lead into the Vienna Convention for the Protection of the Ozone Layer in 1985, and the Montreal Protocol in 1987. And also at the end of the lecture, I'll just mention the Brundtland Report, just as we're moving through a very a seminal report establishing sustainable development as the cornerstone of international environmental regulation. Okay. Might be a little bit cloudy today, but just put your hands up if you walked outside in the sunshine today. So who's been in the light? Okay, come on, that's everyone. You had to walk in light to get here. Okay, even if it was a bit cloudy and you couldn't see your shadow. Okay, so keep your hands up. Go. So keep your hands up if, as you were walking along, you were thinking about how fantastic international environmental regulation is for you and it was protecting you right at that moment. Keep your hands up. All the hands go down. I would say I was ashamed of our class, but no, I'm not. I'm very proud of our class, and it's a natural thing. But people don't think. As you walk outside in the sun every day, international environmental regulation is protecting you and everyone you love and everything around you, even if you don't recognise it, because of its protection of the ozone layer. It's the most outstanding success story in international environmental regulation, and one of the most outstanding international success stories in the history of humanity. Like, what we've avoided was essentially a catastrophe, and this is a tremendous story to tell, because we're going to go on later today to talk about climate change, and we know that there are still huge problems with addressing that, and we can get bogged down in the negatives, get bogged down in the state of the world and all of the problems that we face. It's also really important that we recognise the success stories and that the international community can work together and cooperate to solve things, even with all of the problems about sovereignty and the difficulty of enforcing international environmental regulation. With all of those problems, we can still have tremendous successes. So the context, continuing on from our last lecture, was the 1980s, 1990, a bit of an artificial period, but for our purposes, 4 things to summarise this period. So it's still a period of ongoing growth and expansion in many parts of the world. Government and public concern for the environment is heightened by emerging global threats such as the scientific discovery of the hole in the ozone layer, and also the Chernobyl disaster I mentioned in 1986 in the last lecture. The Brundtland Report is commissioned in that context. The global community seeks a report from eminent experts. Grover and Brundtland was the chair, and her report is famously known as the Brundtland Report. It established the sustainable development as a key international principle. This is also a period of major geopolitical shift as the Soviet Union disintegrates and the Berlin Wall falls. So that's the context. So, looking out, I've shown you this image way back in lecture 1. It's called the Blue Marble, and famous for many reasons, incredibly beautiful. It was one of the first pictures, as I said in lecture 1, that was taken with no shadow. on the Earth. So the Apollo mission that was coming back from the moon snapped it while the sun was directly behind them, and taken in 1972. So we can see our beautiful planet in a lot of its complexity, or get a glimpse of its complexity. We've got Antarctica down at the bottom, Africa, and the swirling massive storms in the Southern Ocean. So we've come down, this picture I also showed in lecture 1, it shows the sun setting over the Western Pacific. It was taken from the International Space Station, orbiting above the Earth, and we can see the layer of clouds and that thin blue smudge on the horizon, which is basically where the ozone layer is, but the blue isn't caused by ozone as such. It's the refraction of light at that point. But essentially what we're going to see is the ozone layer is just above where you see the visible white clouds. And I also mentioned this very famous quote from Carl Sagan. He said, if you covered an orange with a coat of varnish, the thickness of that varnish on the orange would be in proportion to the thickness of the Earth's atmosphere to the Earth. So incredibly small relative to the size of our Earth. So the hole in the ozone layer, and this is just an image of it in 2006, that's a computer-generated image, obviously. You can't actually see the hole, but everyone knows of the hole in the ozone layer, and this is a good illustration of how we can use graphics to represent something and help people visualize. And the hole is a great metaphor. I mean, it's a reality of what it is, but it's a great metaphor that people can easily understand. And the analogy that's often used for ozone is it's like the Earth's sunscreen. So basically like a layer of sunscreen that protects us. So a great little summary of it, and with some beautiful visuals and interviews of key people. It was a Catalyst documentary way back in 2010. Still very relevant though. I've chopped it down to 6 minutes. I just think it's such a great summary of many issues, so I just want to play it for you.
Planet Earth is being cooked alive. Most of the ozone layer has been destroyed by chlorofluorocarbons. No longer are we shielded from ultraviolet radiation. Cancer rates skyrocket. Thankfully, this is a tale about how we chose a different future. A good news story about how to save the world. But for a long time, it seemed the end of the world was nigh. More than 15 kilometres high in the stratosphere, the ozone layer forms a natural sunscreen protecting life on Earth. But when rogue chlorine atoms from synthetic gases are let loose up there, they act as catalysts that pull apart the triple oxygen molecules of ozone.
Ozone depletion in the atmosphere is getting worse.
Since 1975, science knew that increasing the use of synthetic gases like chlorofluorocarbons, or even the exhaust of high-flying Concords, could degrade the ozone layer.
Those inert little molecules from spray cans or air conditioners may present a greater threat than a whole brace of nuclear missiles.
The world was alarmed, but there was little evidence to show the threat was real. Until 1985, that is, when a startling report was published in Nature. Meteorologist Jonathan Shanklin had been working in Antarctica to measure ozone levels above the Haley Research Station with this Dobson spectrophotometer.
I thought it would be helpful to show people this ozone data and compare it with 20 years earlier. And it would be the same. The only trouble was that in the springtime, it wasn't.
That may be the understatement of the century. John and his colleagues had discovered a gaping bite out of the ozone layer above Antarctica.
We were completely gobsmacked, as they say, when we saw this, because it wasn't expected. What we were able to show was that it was a systematic decrease by 30 to 40%, quite a dramatic change, and far outside anything that had been seen in the total record that we'd got.
During that same period, from the mid-70s to the mid-80s, Paul Fraser was recording a steady increase in levels of ozone-depleting gases.
And when the Shankland paper was published, a whole new field of chemistry opened up, because no one had considered that the special conditions in Antarctica would generate this extremely powerful mechanism for ozone destruction.
So what on earth was going on? During the winter, the Antarctic ozone layer gets cold enough that clouds actually form in the middle of the ozone layer, and it's chemical reactions on the surface of those clouds that allow in the spring very efficient reactions to take place that destroy the ozone.
There was a clear demonstration, an industrial release chemical, in minute amounts, relatively speaking, was having a massive effect on a major atmospheric constituent, and it was unprecedented.
Around the world, governments were galvanised into action.
By 1987, we had a Montreal Protocol. By 1990, CFCs were on the path to not being used anywhere. And by the late 90s, they were gone. And all we're left now is the residue of what we put into the atmosphere 30 years ago.
The air I'm breathing here comes straight off a vast ocean, direct from Antarctica. Now, there's just a handful of places in the world where the air is so clean that you can measure minute changes in the composition of the atmosphere. And this is one of them, the Cape Grim Monitoring Station in northwestern Tasmania.
If something's detected in the air here, that's strong evidence it's everywhere. Since the 1970s, it's become the most important station in the southern hemisphere. And for the ozone layer, the outlook is good.
Overall, there's been a significant net decline in what we call effective chlorine, and that's what drives ozone depletion. We are expecting to see an ozone recovery, but these CFCs are very persistent in the atmosphere. The atmosphere will remove them, but it takes hundreds of years. And so the long-term recovery of ozone is a slow process. We probably expect to see ozone recovery about 2060.
On the left is the world we're living with. On the right is the world where CFCs weren't banned. Low ozone concentrations are in blue, average in green.
If you let chlorofluorocarbons increase by 3% each year, starting in 1974, by the year 2065, virtually 2/3 of the ozone layer has been destroyed.
That's not just over the poles, but everywhere. The Antarctic ozone hole becomes a permanent year-round fixture with a twin over the North Pole. In the 2050s, something very scary happens in the modelled world. Ozone levels over the tropics collapse to near zero. Levels of UV radiation triple.
And UV radiation is used to sterilize things. If we'd never regulated CFCs, you wouldn't have been able to go outside for much time at all.
Occasionally I think about, well, what happened if things had gone wrong and we weren't able to carry the popular view, and people just said, oh, this is nonsense, and we want to keep our CFCs, for example. I don't know. It'd be certainly a serious health issue.
Understatement of the century. Okay, so let's just unpack that a little bit. I don't want to dwell too much in the science, but I just really want you to be, and not something I'm going to examine you on at all, but just I really want, for the purposes of thinking about this problem, to unpack some of the scientific issues so that we can, because this is not only a great example of a success story, but it's also a great example of where science and information actually did drive policy and still drives policy. And it's so interesting to compare that to what happens with climate change and how we've got all of this knowledge and information about climate change, and it gets completely, well, not completely ignored, but we're not reacting to it with the level of action that the science says is needed. So I really want us to think about this problem, but I emphasise you don't need to understand the science. I just want to explore it a bit so that we grapple with this for a moment. Okay, so let's think about our atmosphere. Okay, so the number of layers in our atmosphere. The troposphere, the bottom layer, up to about 11 to 12 kilometres. It's where essentially we've got oxygen enough to breathe. It's where all life basically exists. And we know that as you go higher in the atmosphere, the oxygen gets less. So everyone knows if you were to climb Mount Everest, which is just over 9 kilometres, is it 9 kilometres or 880? Anyway, 8,000 metre peaks. I think it's 8,800, isn't it? Anyway, about 9,000 metres high. So most people at that height need supplementary oxygen, and it's very cold. So that's the troposphere. Above that, we've got the stratosphere, the mesosphere, thermosphere, and exosphere going out to about 300 kilometres and beyond, a little bit beyond. So if we just look at those bottom few layers and a visual representation of them. So we've got the troposphere, aircraft flying there at about 8 kilometres, Mount Everest around 9 kilometres, and then the stratosphere. The ozone layer is essentially in the bottom half of the stratosphere, and our atmosphere is just truly amazing. This is a beautiful image from the International Space Station again. Now you can see the clouds there. This must be over the Middle East, isn't it? So it looks like Egypt there and the Nile on the left. Is that what everyone agrees? Is that the Nile on the left? So we're over the Middle East. But the clouds, the white clouds that we see, are in the troposphere. And then on the horizon, the bottom crimson layer, sorry, the bottom blue, little bit of a haze just on the horizon is just above the troposphere where the ozone layer is. It's about 20 kilometres high, and then the yellow-orange layer is an aurora in the thermosphere or exosphere. So they're usually found around 90 to 150 kilometres high, and we normally don't see them unless you're close to the poles. So everyone knows about, the Northern Lights or the Southern Lights that you might see from Tasmania. So that's much higher. But we typically don't think about those layers because you can't see them when you, like the blue marble, for instance. You can't see an aurora, so you just don't even see those layers. So here's a small time-lapse image, and just get an ad.
You know this dance. It's been handed down from one generation to...
Just mute it.
You can skip it.
Skip it now, yeah. You've got that mandatory 5 seconds. Okay, so this is some imagery published by NASA, basically showing a time lapse from the space station as the Earth rotates. And what I really want you to notice is the auroras. Yeah, so all of the white cloud is within 12 kilometres of the surface, so within the thermosphere. I'll pause it there. It goes on for 5 minutes. The link, if you're, you might have seen those little time lapses before. So when we look at, I just wanted to play that because when we look at an image like this, and there's no aurora, the white clouds, as I said, are all within the thermosphere. And we're really familiar with that sort of image, and we're familiar with the clouds, obviously. So similarly, when you look at an image like this, which is a hurricane in the Gulf of Mexico, actually we've seen from Apollo 7 spacecraft in 1968, but all of those clouds are within 12 kilometres, the visible white clouds, and then you've got that blue little crimson bit that's above the thermosphere, so that's basically where the ozone layer is. And similarly here, another big, everything in that hurricane is from 2003, Hurricane Isabel. So, great name. Even got the right spelling, has it Isabel? No, it needs an O. That hurricane is all within 12 kilometres of the surface, and you get that little blue smudge is above the thermosphere, basically where the ozone layer, and similar story there. Okay, so there's a change in temperature with height in the atmosphere that doesn't seem logical. You know, we might assume that it just keeps getting colder as you go out, but that's not actually the case. So within the troposphere it gets colder. So you see there, if we start at the bottom at the surface of the planet, it drops from an average surface temperature is about 15 degrees Celsius. It drops down to a little bit beneath -40 at the tropopause. But then in the stratosphere it actually gets hotter, and it comes back to basically zero at the stratopause, and then drops back down in the mesosphere. And then, you know, it just seems really weird that, okay, we're 90 kilometres out in space, and suddenly it gets really, really hot. So our atmosphere, this amazing thing, does, really complicated, and all these things that are going on that normally we don't even think about. So this is just a graph showing the absorption of UV light. So you've got the altitude above the surface. So remembering that 12 kilometres is the tropopause, and then this is the stratosphere, and this is ozone concentrations in Dobson units, which is a unit named after a scientist that studied ozone. And I've got a little, I think, is it the next slide? No. I've got a slide in a moment, just show, basically, it's only a fraction, it's the amount of ozone actually in the total column of the atmosphere, but it has an incredibly important effect, so that you see there the concentration low. So ozone at ground level is regarded as a pollutant, so, you know, from motor vehicles and those sorts of things, so high ozone levels are toxic. But in the tropopause, in the stratosphere, it's incredibly important for the planet. So you can see the concentration rising up to about 20 kilometres and then dropping off. And you can see that representation there of what happens to UV as it comes through the stratosphere. So basically UVC is basically removed, and UVB is dramatically removed, and UVA makes it through. So we know about, you know, getting sunburnt from ultraviolet light, but it's only the ultraviolet light that actually makes it through the ozone layer that is causing us to burn. So just think of just take a deep breath and breathe out. So you've just breathed in and breathed out part of the atmosphere. What did you just breathe in? Okay, so hit me with it. Your great knowledge of what you breathe every day. What did you just breathe in? Oxygen? Now let's go from the biggest to the smallest. So what was most of what you breathed in? Nitrogen. About how much nitrogen? What's that? 78, 80%. And what does nitrogen do for us? Nothing. It's inert. It's basically just an inert gas, and it's N2, so two atoms in a molecule. And then we've got, what's the next oxygen. Yep, and it's O2, so 2 atoms in a molecule. And as we know, our bodies absorb that in our lungs, into our bloodstream, and it goes to our cells, and our cells use it to break apart sugars. The waste product we put back, so sugars, long strings of carbohydrates, and we expel the waste as carbon dioxide. So that's what we're doing all the time. But what else are we breathing in apart from oxygen? 20% oxygen, so we've now got down into smaller trace gases. Anyone hit me with a few? There's a bit of ozone. There's actually a whole range of things. Put you out of your misery. So argon is nearly 1%. Carbon dioxide is about 300. It's now about 405 parts per million. And then a whole range of other things, including, you see right down there near the bottom, ozone. So we're breathing in and out ozone, and as I said, at ground level, ozone is regarded as a pollutant. So particularly, I think it's motor vehicles that can generate ozone. Okay, so in that, it doesn't include water vapour. So that's the dry atmosphere. So you're breathing in and out those things all the time, and obviously we depend upon the atmosphere for life. So ozone production, essentially it's produced by splitting apart of oxygen molecules by photolysis, or basically cutting by light. So the oxygen is broken apart, and then the single atom of oxygen is unstable and can form together with another oxygen molecule, so O2, to form O3. And that's essentially how ozone is formed. So it typically happens quickly, and so the first part, oxygen molecules are broken apart by light. You get your single oxygen atom. It is interconverted. You can see on the right there in stage 2, oxygen and ozone and oxygen atoms are continually being interconverted as solar UV breaks ozone, and oxygen atom reacts with another oxygen molecule. And then basically you've got a cycle. So I just mentioned Dobson units. So as I said, it was named after a famous scientist who studied ozone. And essentially the idea is you bring all of the ozone above a certain point into a unit. And so if all of the ozone above us right now was to be collapsed down, you'd have about 3 millimetres of pure gas. So it's not very much. So the science that led to the discovery of the hole in the ozone layer starts in really the 1970s with a paper by Molina and Rowland, and these men won the Nobel Prize for this work. So it was a paper published in Nature. It wasn't very long. I'm just going to open it up. To just show you how, so it's 3 pages. So, Nature, you don't get very much space. So there's groundbreaking work. Very complicated chemistry. So the abstract, chlorofluoromethanes have been added to the environment in steadily increasing amounts. These compounds are chemically inert and may remain in the atmosphere for 40 to 150 years, and concentrations can be expected to reach 10 to 30 times present levels. Photodissociation of the chlorofluoromethanes in the stratosphere produces significant amounts of chlorine atoms and leads to the destruction of atmospheric ozone. So you can see some of the chemistry there where they describe what's happening, and then you've got the references as well. So you've effectively got pretty well 2 pages of tightly spaced chemistry. This was the foundation of our understanding of chlorofluorocarbons, as they're most commonly called now, basically damaging ozone. But no one thought it was a major concern at their concentrations, and as we saw in the video, it was only when the work was done a little bit later that they realised that there was special circumstances over Antarctica. So this was an obituary to Sherry Rowland, who won the Nobel Prize. So the death of legendary Nobel Prize winning chemist Sherwood Rowland reminds us of the value of alarmism and the scientific duty to speak out in the face of impending disaster. He saved the world from a major catastrophe, never wavering in his commitment to science, truth and humanity, and did so with integrity and grace. Rowland is one of the true scientific heroes of our time, both for his research and what he did with it. So this is a schematic diagram. Essentially, there's a range of human-produced chemicals which act as catalysts for the breaking apart of ozone. So there's a great book, I think I put a link to it, there's a link certainly in the slides, the Stratospheric Ozone online textbook. If you're interested in the chemistry, go and have a look at it. But essentially it destroys the reaction, and essentially what those chemicals have done is cause a decrease in ozone, not just in Antarctica, so we call it the hole in the ozone layer and it's over Antarctica, but it's now been recorded globally. So this is ozone in Switzerland from 1926, and you can see from about 1980 the trend from being stable to declining. And similarly globally, ozone from 1978 here through to 1994, the trend being a decrease. So the second paper that was really galvanised the world to action didn't come until nearly a decade later in 1985. This was the paper that was spoken about in the short video clip. So large losses of total ozone in Antarctica revealed seasonal chlorine oxide, nitrous oxide interaction. So Farman, Gardner and Shanklin. And again, I'll just open it up to just show you how small this is. So again, it's another letter to nature. Recent attempts to consolidate assessments of the effect of human activities on stratospheric ozone using one-dimensional models for 30 degrees north have suggested that changes of total ozone will remain small for at least the next decade. Results of such models are often accepted by default as global estimates. So they were aware that ozone was affected by ozone-depleting substances, but they were thinking it was going to be a small change. And that's what, remember in the video, that's what the man said. They actually went to show that that was the case over Antarctica. The research, it was pure research at the time. They didn't think there was a problem. The global scientific community didn't think there was a problem. And they just went to do this research to show that there wasn't a problem. And lo and behold, they found the opposite, that there was actually a massive problem. So the inadequacy of the default acceptance that there's only a small change is shown here, is evident by observation in the spring values of total ozone in Antarctica, which have now fallen considerably. Circulation in the lower stratosphere is apparently unchanged, and possible chemical causes must be considered. We suggest that the very low temperatures which prevail from midwinter until several weeks into the spring equinox make the Antarctic stratosphere uniquely sensitive to the growth of inorganic chlorine, primarily by the effect of this growth on nitrous oxide, nitrite ratio. This is the height distribution of UV irradiation peculiar in the polar stratosphere, which could account for the ozone losses observed And so this paper, again, present the results, quite a bit of chemistry, and that's it. And that paper is what then led on to massive global action to basically respond, and so this paper is in May 1985. Okay, so bear that date in mind, because we're going to see that the Vienna Convention, signed by basically every country on the planet at the time, is in 1985 as well. So this is May. By the end of the year, there is an international convention to address this problem. So just some summary of the ozone hole. So it begins to develop in August. So the fully developed by early October, broken up in early December. So obviously southern hemisphere, from winter through to spring. First began to appear in the early 1980s. Compared to the 1970s, there's a 60% reduction of ozone over Antarctica in early October, 100% loss of ozone in the 12 to 20 kilometre region over Antarctica. Some ozone remains both above 20 kilometres and below 12 kilometres. It covers a massive area. So these are some of the computer depictions of it. So the top left is the 70s, the top right is the 90s, and then the bottom one is showing the difference. And you saw that sort of image in the little video clip. So it's clouds in the stratosphere, and it's on the surface of those clouds that you get the reaction that catalyzes the breakdown. It's not just, so UV light isn't the only impact that has been caused. So this was a paper from a few years ago. It's not just sunburn. The ozone hole's profound effects on climate has significant implications for the southern hemisphere ecosystems. So this talks about wetter summers in South America, warmer, wetter summers in South Africa, in Australia, warmer, wetter summers, wetter summers in Australia, increased wind over the Southern Ocean, a whole range of effects. And it's a really interesting paper because they try and think about what changes, and they try and present the changes in 4 dimensions, so the 3 dimensions plus the dimension of time. So this is an interesting depiction of the different circulation cells in the southern hemisphere. And then I know this looks complicated, but what they're trying to represent here is the complicated changes in the 3-dimensional world in time, and they're really difficult to conceptualize. So here they're showing Antarctica on the left, and how the jet stream changes in the jet stream then affect ozone depletion, affecting changes in the jet stream, changing essentially ocean circulation. Don't want to get bogged down in that complexity, as I say. So this paper in 1985 and this research just was a alarm bell that rang in the 1980s. Now let's just think about this time again. So I keep emphasising the importance of understanding the history and context of these conventions. So we'd had the 60s and 70s where environmental concern became much more prevalent, and a range of important treaties were agreed to. The world was still highly concerned about environmental damage in the 80s, and then this paper basically said we're changing a major component of the atmosphere, and the global community accepted that and responded immediately. So the Vienna Convention for the Protection of the Ozone Layer was signed in 1985, and it establishes a framework, much like the United Nations Framework Convention on Climate Change. It just establishes an agreement to agree, but the detailed obligations are left to be worked out in the future. So that then led to the Montreal Protocol on substances that deplete the ozone layer by 1987. So within 2 years, you've got the details fleshed out. So an incredibly fast reaction from the global community. So you can get heaps of information on the Montreal Protocol website. Huge amount of information. There's 197 parties. It was the first treaty to ever achieve universal participation. It's amazing. And as we saw with the Ramsar Convention and the World Heritage Convention, the detail gets brought together in handbooks. So here's just covers of the 9th edition of the handbook for the Vienna Convention for the Protection of the Ozone Layer, and on the left, and then the handbook for the Montreal Protocol on the right. And they're big, complicated documents. So if you were working in this area, say you worked for government, and your role was implementation of these obligations, those handbooks would be a fundamental reference point for you. We don't need to look at them though. Details aren't important for us, because I'm just going to show how that is flowed through into essentially the world acting collectively, but also essentially society doesn't even realise that these things are happening. So some common ozone depleting substances and their uses. So chlorofluorocarbons, or CFCs, are famous. So refrigerants, cleaning solvents, aerosol propellants and blowing agents for plastic foam manufacture. Halons, so fire extinguishers, fire suppression systems, explosion protection. Carbon tetrachloride, production of CFCs, it's a feedstock and used for solvents, dilutants, fire extinguishers. Methylchloroform, an industrial solvent for cleaning inks, correction fluid, and methyl bromide, so a fumigant. So key point I'd make here is, everyone knows about CFCs, but there's a whole heap of other ozone depleting substances that most people don't even know about. So the basic reference point that's used is trichlorofluoromethane, or CFC11. Now, I don't want to get bogged down in the chemistry, but has everyone done basic chemistry, or it's, even if you haven't, what I want to emphasise is how useful chemistry is for understanding these problems. So here we've got it's a carbon atom, so obviously just a diagram of it. A carbon atom with 3 chlorine atoms and 1 fluoride atom. So this was used as a refrigerant gas, and I think it was also an aerosol propellant. Aerosol. Was it aerosol, not refrigerant? It was aerosol. So it was basically used. So if you've got a can, so I've got these are obviously, this is some of the bug spray we had yesterday. When you spray, but this one's just a little push one. There's no propellant in it. But if you've got a spray and like a hairspray, and you push it down and the spray comes out, well, or a deodorant or something like that, it's been pushed out by the propellant. So the propellant that was widely used up until the 1990s was CFC11, and you can see its production increasing exponentially from 1960, and then it levels out about 1970, and then basically so here's 1990, so this is 1985. It still increased for a few years, but by 1990, basically it basically plummets to, by 1995, basically not being produced around the world. So, and here's CFC11 in concentrations measured from 1977 to 1995. You can see it levelling out there. So, and that's in parts per trillion. So CFC use in 1974, most of it was used for propellants, so 70%, and then blowing agents, cleaning agents, refrigerants as well, about 18%. So your stock standard aerosols. Now, of course, we now still have aerosols, and you can go into a shop and buy a deodorant or a hairspray or whatever. Does anyone go and check the labels that it doesn't have chlorofluorocarbons in it? Anyone ever done that? Do you think you have to? Should we be doing that?
Air conditioning, when you buy an air conditioner.
Yeah. Should you check?
Yeah.
You should check?
Yeah.
Actually, you don't need to. You don't need to even check, because, when we're talking about trade and we said labelling is such a weak measure because most people don't read it, well, we don't play around with CFCs anymore. We don't make it a label choice. We don't give the consumer a choice. They are just banned, gone. You can't buy them. You could not walk into if you went to the local supermarket here, you could not find one can on any aisle that had a CFC in it. They're just completely banned. So you don't have to read the label. So you can still use these things, but they don't have ozone depleting substances in them. They've got other gases. So fridges as well. So, the basic thing with an electric fridge is there's an electric motor that compresses a gas, and the gas basically is the expansion and compression of the gas that basically draws the heat out. So the electric motor compresses a gas, goes around and basically draws the heat out and keeps your fridge cold. So that's fine, and you don't want to lose the gas. The problem happens though when the fridge breaks down and goes to landfill and gets crunched up, or it gets a leak and the gas gets out. So those are common things that had ozone depleting substances in them, and you can see why. Like, CFCs is a common term. It's one of the most prolific ozone depleting substances, but ozone depleting substances covers a lot more than just those gases. So the Vienna Convention, if I just summarise it, so obviously signed in Vienna. So starts with standards of structure we've seen. And so I haven't put up the preamble, introductory things saying there's a big problem, we need to fix it. But Article 1, definitions. The ozone layer means the layer of the atmospheric ozone above the planetary boundary layer, so above the thermos of the tropopause. And then adverse effects means changes in the physical environment or biota, including changes in climate, which have significant deleterious effects on human health or on the composition, resilience and productivity of natural and managed ecosystems, or on materials useful to mankind. So we've still got sexist language in 1985. Article 2, general obligations. The parties shall take appropriate measures in accordance with the provisions of this convention and of those protocols in force to which they are a party to protect human health and the environment against adverse effects resulting or likely to result from human activities which modify or are likely to modify the ozone layer. So that's a general obligation, but you can see how it's linked to the protocol or things that come after. So, we've talked about terminology. So treaty and convention are used interchangeably for international agreement. Protocol is typically a subsidiary agreement under a treaty or convention. So that's why we've got the Montreal Protocol on substances that deplete the ozone layer is a subsidiary document to the Vienna Convention. And similarly, the Kyoto Protocol, the full title to the Kyoto Protocol is the Kyoto Protocol to the United Nations Framework Convention on Climate Change. And now we've got the Paris Agreement. It hasn't used the word protocol, and it's a change in language that's probably meant to reflect that it's not intended as legally binding. So there's subtle changes in language. But protocol generally, if you see the word protocol, it means it's subsidiary to a treaty and created within the treaty framework. So the Montreal Protocol, 1987, definitions, and you can see it's linked to the convention. So convention means the Vienna Convention. That's interesting, isn't it? It was adopted on the 22nd of March 1985. I had thought, I'm just thinking of the chronology there, because the paper, they must have basically pre-published the. So this is the paper, the 16th of May 1985. So the convention's even before the paper comes out in Nature. And presumably it would have been only the year, so that their results would have been the Southern Hemisphere summer of 1984, I presume. So the key point is very, very quick, the response to this research. So controlled substances means substances in Annex A, B, C or E. So similar to, remember when we looked at CITES and you had the appendixes? So a lot of the detail gets moved to out of the body of the document. So Article 2, capital A, CFCs, and it's just as an example, obviously don't need to remember the detail, but just to see the sort of language. Each party shall ensure that for the 12-month period commencing on the first day of the 7th month following the date of entry into the force of this protocol, and in each 12-month period thereafter, its calculated level of consumption of the controlled substances in Group 1 of Annex A does not exceed its calculated level of consumption in 1986. By the end of the same period, each party producing one or more of these substances shall ensure that its calculated level of production of the substances does not exceed its calculated level of production in 1986, except to that, you get the idea. So what's 1986 used as? A baseline, yeah? It's a reference point. And why do they choose 1986? So this is being agreed in what year? No, this is 1987 now. So this is the Montreal Protocol. So they're using a reference point of the year before. So why are they doing that? Because it's the most up to date, and it means that also that essentially, assuming that you can calculate the amount that was produced in that country with integrity, then it can't be changed. It's a fact that you can verify, whereas if you make it let's just say the baseline was to be 1988, what's to stop a country going out and massively producing more so that it gets a higher baseline? So anyway, calculated by reference to a baseline, and also what does that mean in terms of you've got a common baseline, but is that going to mean that every country can produce the same amount as each other? No, it gives you flexibility for however much that country produced in 1986 is the baseline for that country. And so a small producer doesn't get the same quota or baseline as a big producer. But it's fair in the sense that whatever you were producing last year, that's your baseline. Okay, now Annex A, just as an example, controlled substances include CFC 11, CFC 12, and it's got an ozone depleting potential of 1. So CFC 11 is the reference point, and other chemicals are compared to CFC 11.
So, sorry, you're saying the country that was producing it, not consuming it, producing it?
Yes, so, consumption. Actually, no, we've got both there, haven't we? So the first part is consumption, and the second part is production. It's just a long, lots of legal writing is really terrible to read. At least there's a few full stops there. The old style of legal writing used to be just continuous, no full stops, no commas, just basically you'd have 12 or 15 lines of text. So anyway, so baselines for both consumption and production. So we've got a range of different CFCs, halons as well. So, and if you actually went and looked at the list, they're really, really long. I'm not going to put them all up. All I wanted to put them up is to just illustrate to you that there's all these chemicals that are listed in them. Obviously very technical, and particularly, even if I did chemistry many, many years ago, even if you've got a basic understanding of chemistry, it still looks complicated. So this table summarises the phase out. So ozone for different ozone depleting substances. So for CFCs, for developed countries it was phased out by 1995. For developing countries by 2010. Halons, similar years. Carbon tetrachloride, methyl chloroform, hydrochlorofluorocarbons, hydrobromofluorocarbons, methyl bromide, and bromochloromethane. Some of the ones that were really, because what they gave time to get rid of them. Why do you think they gave time to get rid of them?
To adopt new technology.
To find alternatives for them. So basically, let's phase them out, and quickly, but allow time to find other things. So some of the ones that have been really hard to find substitutes for have been some of the, as I understand it, some of the agricultural fumigant ones. It's been really hard to find similarly effective fumigants for killing insects from grain and those sorts of things. Also, some of the fire extinguishing chemicals were very hard to find non-ozone depleting substances that basically were similarly as effective. So they've been some of the harder ones, but refrigerant gases, they found substitutes for them quickly. Okay, I've emphasised numerous times that you've got to implement this into national laws. So just as an example, in Australia we've got the Ozone Protection and Synthetic Greenhouse Gas Management Act, 1989. So a couple of years after so this is Australia enacting law to fulfil its obligations under the Montreal Protocol. I won't go into the details, but essentially Australia's just basically replicated that into it. What it's required to do under the Montreal Protocol is effectively implemented through legislation. Okay, so the effective chlorine under the Montreal Protocol. So basically, the red dotted line shows what it's thought would have happened if the world hadn't acted, and then what's actually happened under the Montreal Protocol is the effective chlorine concentrations have levelled and gone down. So you've got there the reference future. This is the world avoided. So by 2060 it was thought that total ozone would collapse. By 2060, that's the black line. And then the red line is the recovery of ozone globally. By about 2060 it's expected that ozone will have recovered. And the key thing is we avoided the collapse of the ozone layer, not just over the Antarctica, but around the globe. So that's the UV index. So the black line again is what the world avoided by 2060 if we hadn't basically recognised there was a problem and just kept doing what we were doing or acted effectively. Basically UV would have not just obviously for humans, it's not just that we could all live in, underground in a concrete bunker and, have some sort of life, but, all of life, everything, marine life, all of that would just be completely cooked. So, yeah, we would have basically, catastrophically damaged the entire ecosystem. Just mention we're still dealing with the legacy. So even though these things have largely been phased out, we still have, they're going to remain in the atmosphere for many decades. And so just in 2011 was the first hole over the Arctic. The Arctic got cold enough in around Christmas time to basically form clouds in the stratosphere, and so the same reaction, the same catalytic reaction happened on those clouds. And there was again, if you're interested in this topic, there was a big report released in 2014, basically an assessment of how we were going, and yeah, it found that basically the ozone layer is recovering, that the overall framework has been successful. It requires ongoing implementation and and monitoring, but yeah, the overall framework has been successful. So chlorine sources of gases, CFC 12 there you can see basically unchanged, but CFC 11 dropping off, and yeah, this is all just from that report, basically saying that effective chlorine is expected to come right back down by about 2080, and the ozone to recover by that time. So, and then there was a whole heap of news stories around that time. I just got some of the headlines here. So there's a good news story. Fragile ozone layer shows first signs of recovery. UN says, good news, the ozone layer is showing signs of improvement. Scientists say ozone layer is recovering. And yeah, this is just an article writing that up. Emergence of healing in the Antarctic ozone layer from last year. So just to summarise all of this, again, I don't want you to worry about the chemistry as such, but I wanted to go into it a little bit to illustrate how science and data can drive policy, can drive effective action. And also, I really wanted just you to take away from the response to ozone depletion that the world actually did this well and worked together, solved this problem. We've still got the legacy of it, but it's not like, this is a very different situation from, when we talked about MARPOL, how the world, there was this, after Torrey Canyon, there was an agreement, but it didn't enter into force, and it took another disaster before the world acted, and it's a basically disaster-driven model. So here, yes, there were impacts, but we avoided the catastrophe, and the global community came together, so reacting to science saying there is a big problem, but before, it wasn't disaster-driven, it was proactive, comprehensive, very quick, and a really great success story. So yeah, today when you walk outside in the sunshine, think about how international environmental regulation is protecting you and everyone that you love by protecting the ozone layer. And people don't even think about that. They don't. I remember actually, you might see it on last year's exam paper when we look at that, but there's a literally a quote from Donald Trump, where he says, he basically says, how can, I spray, hairspray, and I don't think he used hairspray, I spray something on myself in my apartment which is completely sealed, how can I, damage the environment, in one of his speeches. So he was basically attacking the ozone treaty. And so the last year's question asks, the new President Trump decides to withdraw America, or the United States of America, from the ozone convention, discuss the process of, how this goes about, something like that. It was a question based on that, but it literally was a quote from him. It was just like, but apart from, crazy people that deny, reality and, live in this alternative facts sort of universe, it's just, just such a fantastic story of what we've done. And yeah, so international environmental regulation protects you every day of your life, whether you're aware of it or not, and will for every day of the remainder of your life. Okay, so that's ozone. Just want to mention the Brundtland Report, 1987. So again, think of the context. The world has just had this wake-up call about ozone. It's following on, decades of, big disasters around the world, oil spills and those sorts of things. 1986 was the Chernobyl nuclear disaster, which spread radiation across Europe. So Brundtland Report was commissioned by the global community to, they formed the World Commission on Environment and Development. Grover and Brundtland was appointed as the chair, and the report, Our Common Future, is famously known as the Brundtland Report. And this is just an extract from it. Sustainable development is development that meets the needs of present generations without compromising the ability of future generations to meet their needs. At a minimum, sustainable development must not endanger the natural systems that support life on Earth, the atmosphere, the waters, the soils, and the living resources. So that's sustainable development. And it's commonly shown in this sort of diagram, sort of three overlapping circles of environment, social, and economic. I much prefer this one, which is the bullseye diagram. So there's a famous US Senator, Gaylord Nelson, who died a decade ago, but he said the economy is a wholly owned subsidiary of the environment, not the other way around. Could I do that with a US accent? The economy is a wholly owned subsidiary of the environment, not the other way around. How's my US accent? Pretty bad? Okay. So environment, society, economy, not, three equal circles, As you can say to economists, try holding your breath and see how long you last. I love this cartoon. Apologies to Gary Larson. So I'm not sure if other people like he at least when I was young, and as I said, dinosaurs roamed the earth. Gary Larson had the Far Side series. I'm not sure if you guys have. It's not as ubiquitous anymore, but I saw this on a card in a newsagent. And it didn't have ecologically unsustainable development in that bubble up there. I've added that. It just had a green sort of top. But I remember looking at it and just thinking, that is just such a great representation of it. And I love how with Larson, he can get just such expression with just like a dot and a few lines. Like look at that. Look, see, you get the goldfish that's got the baseball bat. And you can just see the, holy shit. In his face and his little mouth, and then the one with the baseball mitt, who obviously didn't catch the ball, and they're thinking, what are we going to do? Are we going to throw ourselves into the hole and plug it, or how do we? And I love this cartoon because I think it actually represents the problem on so many levels. Because I think a lot of politicians, like say Donald Trump or Tony Abbott, or these people that are fighting against, taking action on climate change, they think this is like a game. Like, we're just playing catch. And, technology is going to be able to fix it. That, we don't have a major problem. So, yeah, ecologically unsustainable development. So, are we achieving sustainable development? What do you guys think? No? Who's for no? Who's for yes? So we've got about 70% no's and none yeses. Now my math isn't so good, but 70% and 0 doesn't add up to 100. So let's try it again. Okay, you've got three options. You've got to commit. So you can either commit to yes, you can commit to no, or you can do a handstand at the front. Okay, so are we achieving sustainable development? Who's for yes? No hands. Okay, who's for no? And we've got, I thought you were going to do a handstand.
Working to achieve the sustainable development.
Okay, you think my questions are unfair?
We're on the way, but we haven't achieved it yet.
We haven't achieved it yet. My questions were unfair. Okay, well, can we achieve sustainable development in a culture focused on consumerism and economic growth? What do you think?
You can put a spin
You can put a spin on it. This is an article from Nature, actually, from a couple of years ago. Australia is free to choose economic growth and falling environmental pressures. These guys effectively were arguing we can achieve sustainable development by... I thought it was a load of crap myself. But anyway, it's published in Nature, so I'm being too flippant there. It was an interesting paper. I just didn't think it reflected reality. But more to me, the question is, if we're not achieving sustainable development, should we replace it as an overarching policy objective? And then the question becomes, well, if we're going to replace it, what do you replace it with? Because the big thing that sustainable development achieved was it gave environment a seat at the table, where the only seats previously were economic growth and social well-being, in terms of living standards. They were the only seats at the table for most governments. So sustainable development was basically saying, hey, environment actually needs to be looked after, and that was the big achievement for the Brundtland report and that whole sort of, trying to change a mindset. So I think my question was unfair, because there is some good news. We are achieving sustainable development in some areas. So ozone protection, can I just give you a story? So when I started my PhD a long time ago, I started it wanting to evaluate environmental law in Queensland, and I thought our laws are really bad, terrible. We're doing a really bad job. And then, as I was doing my PhD, because I basically set up a topic where I thought I was going to basically criticise it. And then I think it might have been a trip to Springbrook Miles, or it might have been Lamington, but I remember walking in a national park, probably was Lamington, and thinking, is our system, would it be better or worse if we didn't have national parks? And I thought, well, it would be worse, definitely, for protecting the environment. But, this national park is a valuable thing, and it's, leave aside climate change, but, we've protected the flora and fauna within this area pretty well. And that's a good thing. So then I thought, well, our system would be worse then if we didn't have this. And then I suppose through my PhD I became more balanced in realising there are actually good things in our system. It's not just all bad. So in that context, I think it's important, and I'd emphasise for you with your research that your evaluation shouldn't be 100% success or 100% failure. It's going to be somewhere in between. However bad what you're looking at is, or however good it is, there is a range of success. It's not total, it's not black and white. So the good news is for sustainable development, we are achieving some really positive outcomes. And ozone is the great one. We've demonstrated in the past an enormous potential to save major global problems. Okay, the bad news is that overall we're not achieving sustainable development, and there's no simple or clear path to how we achieve it in the face of population growth and modern cultural paradigms built around unending economic growth and increasing consumption. Okay, so we haven't really talked about population growth. There aren't any conventions on it. Unlikely that there will ever be a convention on it. You see the problem we have in a country like Australia, even agreeing that people can marry who they want to, let alone trying to control the number of children that people might have. It was, there's so many religious and cultural taboos to that. So we use soft mechanisms to control population growth. So what's the best, does anyone know the best mechanism we've got for controlling population growth globally? Education, not just education. Education of women. Education of women is the best mechanism we have got for controlling population growth, because a empowered woman basically is much less likely to have a lot of children. So education of women is the best, and in terms of I mean, generally culturally acceptable, unless, you know, you live in a Taliban-controlled area or something like that. But, you know, generally it's a relatively socially acceptable policy. But apart from that, we've got very little that we can do about those things. And obviously we've got, you know, you go and look at any newsagents, you know, and magazines covered basically promoting consumption. So there's no easy way that we're going to solve this. There's also a widespread assumption, I'd suggest, that technology will solve all of our problems. And I put up this picture of Star Trek to illustrate that. Okay, so sure, you know, we've all seen Star Trek, you know, great fun. And, you know, there's plenty of movies around. Was it The Martian recently with, who was it, who was stuck on Mars and, not Brad Pitt, was it Brad Pitt? Was he stuck on Mars, The Martian? Matt Damon. So, you know, there's plenty of movies where, you know, we get, you know, humanity is, you know, spread out into space. So we can have in our mind that that is our future, the future of humanity, but of course all of those things are just filmed in a studio somewhere. The reality is we have great difficulty even getting to our moon. So I hope that, you know, one day humanity will go out and explore the universe, but as far as we know right now, this is the only place we've got. So we better protect it, like being in a lifeboat and there's sharks all around you and you can't swim, you know? The lifeboat's got a hole in it, you better plug it because there's nowhere else to go. So technological optimism, so it's, you know, technology is really valuable for us, but we can't just assume technology will solve it. You know, like look at, you know, say North Korea now, or nuclear weapons, you know. What's the technical solution to nuclear weapons or nuclear proliferation? Is there a technical solution? There isn't any technical solution. It's just not possible. So we don't think we're going to have a technological solution to that. Why assume we're going to do it for climate change? So technology has an important role in managing environmental problems. So, you know, the technology in developing alternatives to ozone depleting substances, that's a great example of technological success. But technology alone can't solve all environmental problems. Behavioural change is also critical. So if we think about ozone, it wasn't just technology. We actually imposed legal restrictions phasing out the use of ozone depleting substances. So that was vital to the success of the overall scheme. So you can't go into a supermarket now and buy an aerosol can or you can't buy an air conditioner that's got ozone depleting substances in it. So it's not just that technology has allowed replacements, it's also the law doesn't allow you to do it, and we've just basically banned them. So technology and behavioural change is important, and obviously law and policy has an important part in that. So I'll just summarise it in this way. So we're not achieving sustainable development, I think, in relation to climate change, you know, in comparison to how we we solved the Vienna Convention. And I suppose, can I just blank that for a moment? You think in 1985, you know, it's easy to look back now and say, oh, you know, we found solutions for all of the technology. But in 1985 and 1987, they didn't have ready solutions. You know, they committed to phasing these things out and finding and working out how to do it later.
Would it succeed now?
Yeah.
That's a question. Would Vienna and Montreal succeed now?
Yeah, it's actually a great question. And when we get on to, in the next lecture, we're going to get on to 1992 and the Rio Conference and the agreement to the Biodiversity Convention, the UNFCCC, there's all these, and that actually is the high water mark of international cooperation on environment, and since then there's largely been a retreat. So a lot of people say don't go back and try and reopen negotiations about those because you wouldn't actually get agreement to them today. you wouldn't get the US signing up and being able to ratify the UNFCCC. It couldn't do it today. So, if the ozone hole happened today, we'd have no doubt, that's fake news from Trump and Republicans and industry, and, there'd be a whole debate about what reality to accept. So, but in relation to climate change, I've thought about this a lot, and to me, there's two things. We're not achieving sustainable development in relation to climate change because, A, we've not convinced the majority of people of the extremely serious nature of the threat if we follow a business as usual path over coming decades and continue to burn enormous amounts of fossil fuels. And secondly, we haven't convinced the majority of people that there's a positive alternative future without burning fossil fuels that maintains jobs, homes, food supply, and comparable lifestyles or acceptable restrictions on lifestyles. I think there's those two components. I was chatting with someone, was it yesterday when we were walking, about research into and climate change and the balance between scaring people and being positive. I can't remember who was I was chatting with someone about that. I think that both components, you have to recognise the threat, but also have a positive message that we've actually got a really great future with, because if you think about with climate change, there's so much work in repowering our society with renewables. There's so much research to be done, so much manufacturing to be done, so many jobs in actually changing society. It's a massive job opportunity, but at least in Australia, it's restrictions on fossil fuels are seen as this huge threat. So there's no simple solutions, but our path forward, I think, is hope and vision are important. So this is a great quote from a fellow in the US saying, "Our vision of a sustainable future must inspire rather than burden, and thus should be partnered with fine art, great literature, and powerful music." Lovely idea. It must lead rather than support the status quo. It must build rather than merely struggle to maintain. It must counter fear with a luminous path forward. It must provide brilliant, pragmatic hope when the future seems devoid of options. Lovely idea. Obviously, we're in the age of a horrible person in the US, and it's hard to sort of have such lofty ambitions. But I really believe that hope is a really important part for us to maintain. And we also need to be pragmatic and engage with the reality of our cultures. This is, sure, a lot of people have seen Abraham Maslow's hierarchy of needs, famous in psychology, criticised, a lot of it's done in 1943, a lot of work's been done since then, but he basically, remember I was in the army years ago, and this was, basic training about psychology was the psychology of needs. So basically, people are driven first, if you're hungry and thirsty, you can't think about much else, and if you're unsafe, then, that's your priority. It's only when you satisfy people's food and water and safety needs that you then move on to higher level needs such as friendship, self-esteem, morality, those sorts of things. So we have to still satisfy, feed people, give them a clean environment, satisfy those basic needs before we can solve the bigger problems. So we've got to be pragmatic. I really this is all just building on sustainable development and where we've gotten to now. A great book, I really like this author, Van Jones. He's a US writer, The Green Collar Economy. And the basic message in that book, you can go and buy the book, but the basic message is this: to succeed, environmental problems must be linked to jobs and poverty alleviation. If you don't do that, particularly the jobs and poverty, the poverty alleviation aspect, you won't get the social support for it. That, if you only make it about the environment, then people who don't have a job and are really poor, they're not going to be on board, and then you won't have the political support for it. So whenever you're, in your futures, you're looking at environment programs, it has to be linked to be ultimately to be successful, if it's not linked to jobs and poverty alleviation, then it's not going to be successful. That's his message, and I think he is 100% right. So, so I've written, so based on that sort of idea, this was an article I wrote in The Conversation years ago, and I mentioned it it was written about, a news item came out about how China had made environmental protection a fifth pillar of its economy, and it was going to put something like 8% of its GDP was going to go into clean energy production and cleaning up its environment. It's an enormous amount of its GDP. It's just staggering. But it was the time when Tony Abbott was just about to get elected, and I wrote this article basically to try and give parallels to Australia and say, actually, it'd be a really good idea if we made environmental protection, recognised it as a job creator as well. So environment protection industry, a job creator. So trying to capture the key message in the title, because most people don't read past the title. So if you can give them the key message, you've at least, tried to communicate, or that's your best opportunity to communicate with people. Job creation is really important. This quote I put up earlier also, you cannot protect the environment unless you empower people, you inform them, and you help them understand that these resources are their own and they must protect them. And we talked about this, so not seeing environment as in opposition to jobs, that environment is the foundation that we build our society on. That's one metaphor that can be used. Or the environment is the taproot, the basic thing that keeps this tree alive, where the fruit are things like jobs and a stable society. So hopefully humanity will one day travel to the stars and explore the universe. However, as far as we currently know, we are alone, and this is the only planet we have. There is no plan B. So this is a quote from the President of the Maldives. The last generation of humans went to the moon. This generation of humans needs to decide if it wants to stay alive on planet Earth. So, just wrapping up, in this lecture we talked about the ozone layer and the Vienna Convention and Montreal Protocol that protecting it, and also the Brundtland Report. Can I summarise the lecture in 3 points? So the response to ozone depletion is an international success story, and remember it. Don't lose sight of it, when we go on to look at climate change and the problems that we still face. It's the most outstanding example of successful international environmental regulation. The global community responded rapidly and largely proactively to scientific evidence to create a regime that appears to be effective in halting the loss of the ozone layer. And that has profound implications for us right now, right today, everyone you love, your kids, your grandkids, everyone that will ever come after us. Profound implications. Sound scientific knowledge and understanding of the nature of any problem is the foundation to effective international regulation, and it can be really complicated. And following the Brundtland Report, the concept of sustainable development emerged as the overarching goal of international environmental regulation. So if you wanted to look at ozone, there's heaps of information on the website, but you don't need to for our purposes. So every time you step outside in the sun, international environmental regulation is protecting you, whether you realise it or not.